radius, and isn't this right here our R inner radius? Yeah? So following that idea, what is the volume of this piece, this one piece? You can either look at this one or this one. I'm going to write it down over here, though. It'll be pi. So the volume of this is, you said pi, and then you said what? Okay, I'm going to do parentheses here. F of x, that squared, minus g of x squared, and then h, but what's h for us? Dx. If we go back up and look, we said the volume of a washer was pi times the outer radius squared minus the inner radius squared times h. Be careful on this, because students will make this mistake. They will do this. That is not the same. It's not the difference between the two squared. All right? You're not taking the difference between the two and squaring that. You're taking each one and squaring them, then taking the difference. So, not the same. Questions? That's the volume of one slice. What would the volume of the whole solid be? The volume of the whole solid. We would say the integral from a to b. What's going to pop out? Pi is going to pop out. And then we're just writing this formula down, right? That's all we're doing? See, so once you find the formula for one slice, you're in business. Because you can generate the formula for the total volume by just throwing your integral sign on it. Are there any questions? No. It will always be dx. The question was, will this ever be like an actual height? No, because dx is this infinitesimal width that's going to go to 0 in the limit. It's shrinking. So this is always changing, so it can't possibly ever be a fixed number. Did I forget my drink? I forgot my drink. Oh, thank you. All right. And my keys. Crazy. You didn't put anything in this, did you? No. You didn't take anything out, did you? All right. My 9 a.m. class is convinced that I drink whiskey every single day. I don't know where that... It's because my Crown Royal book bag that I use on that camera. They always give me a hard time about that. All right. Here, I mean, this is it. This is the basic idea, all right? So I think we need to do some examples, don't you? Keep in mind here, as I go through these examples, the main idea right now is for you to be able to generate the formulas. The functions I'm going to give you that we're going to look at are going to be very simple. And that's because I don't want to get bogged down on the complex functions. That's what your homework will be for. The homework will have you think a little bit more about, how do you draw the functions and where do they intersect and things like that. But just for this, I need to just give you some examples so you can see the method.
I have a question.
Yes?
That formula that you gave us, can it be split up into two integrals?
Can the formula be split up into two integrals? What do you think?
Yes.
Yes, it can.
Because it's not like that anyway, so it makes a difference?
Well, if you split it up into two, the only drawback I see is that when you do the antiderivative and plug in the two endpoints, you're going to do like something minus something, right? And then on this one, you have to do it again, something minus something. As opposed to doing it all at one time, you're only going to have to plug in those numbers one time. Does that make sense? So this is okay, but it's just, I think, a little bit more work. All right, so let's do something relatively easy in terms of the functions. All right, rotate, or find the volume, sorry. Find volume. Find volume of solid generated by revolving, can't spell, the region bounded by y equals x and y equals x squared about the x-axis. We're going to have to rotate that region around 6 different lines. We're starting with the x-axis. Don't worry, it's going to be fine. It's going to be fine. We'll have to rotate that around the x-axis and the y-axis and 4 other things. Don't worry about it. Baby steps, baby steps. Walk before you run. All right. Let's start by figuring out what the region looks like, right? So this step is pretty much what you were doing when you were asked to find the area between 2 curves, right? You have to find that region. So I started out with some pretty basic functions here. Y equals x. I'm going to use colors today. See, y equals x. And y equals x squared. These are both functions of x. Right? They're both functions of x. If I were being asked to find the area, I would leave these as functions of x, right? And I would draw a vertical rectangle, wouldn't I? If I were being asked to find the area. And the same thing is going to happen here with my rectangle and rotating it around the x-axis. There's my arbitrary rectangle. Remember, that moves, right? That moves from left to right. While I'm here, do we know this intersection point? That's 1. And then 0 here, right? So that we've got. My axis of rotation, let me put that little kind of curly arrows like that to let everyone know I'm going to rotate that. And I brought a special neon orange. It even says Expo Neon. My neon orange is going to be my region that I'm rotating. That probably won't show up on camera, but it's nice, isn't it? All right, so that region's getting wrapped around the x-axis, right? Okay. I'm going to come over to the side. I'm going to draw my axis of rotation, which is the x-axis, right? So it's also the x-axis, which is solid. And I'm going to label that. I'm going to take the rectangle and bring it over here, like this. And then I imagine wrapping it. Now you don't necessarily need this picture, but it doesn't hurt us to draw it. I'm going to get a washer when I do that, right? What are the most important things that you need to find if you're going to use this formula? Think of the formula for the washer, way from the beginning. Outer radius, inner radius, height. But height is going to be always pretty obvious. In this case, dx, right? So let's start using that terminology. Outer radius, inner radius. Outer radius, inner radius. So let's discuss outer radius. My outer radius is the distance from the axis of rotation to the outer edge of the rectangle. So here's a way I can try and illustrate this. Like if I was standing on this axis of rotation, so here I am standing, that's my head, my feet are at the bottom on the dotted line. Then here's that same picture here. Dotted line, got a rectangle laying on the ground over there. Yes? Do you see it over there, laying on the ground? Okay. If I get a measuring tape and I measure from here out to that edge, I need to know how long that is. So for this particular problem, it is here to here, right? And what is that for us? It's the blue function. That's why I did it in blue. And that's just x, isn't it? So I'm even going to write this down over here just for my own reference. The r out is just x, right? What's the inner radius? That's the distance from the axis of rotation to the closest edge of the rectangle, which is that distance, which is dictated by the bottom function. So for us, that's just x squared, right? So the r in is x squared.
So it's kind of like before it would be like the g minus x, still kind of like the same thing.
Yeah, with the areas, look, with areas, weren't we always, when we were in this situation, weren't we just saying like top minus bottom? Like top minus bottom, top minus bottom. Yes?
Yeah.
Top. Throw that idea out, okay? We're not going to be sitting here going top minus bottom, top. We're going to be doing r out, r in, radius out, radius in. That'll get you in trouble, as you'll see as we move through. If you always do the top minus bottom for these problems, you're going to get them wrong. So just think about the geometry of what's happening here. You're standing there, you're measuring, this distance is x, this distance is x squared, right? All right, so that's it. We're there. There's not anything else for us to do. We know how wide this is, that's dx, right? We know that if we can generate this formula for this one slice, then putting the integral on it will give us the whole thing. So let's go ahead and do it. I'm ready for the total volume. The volume will be pi integral 0 to 1. Okay. So we're going to take the outer radius and we're going to square it. Minus the inner radius squared, which is x to the 4th dx. Pardon? You could take out an x squared, but think about what are we about to do with this? About to integrate it? So I would just integrate right there. Does this seem straightforward to you? Okay, let's go ahead and finish this problem up. Pi's out here. What's the antiderivative? 1/3 pi, 1/3 x cubed minus 1/5 x to the 5th, evaluated 0 to 1. Plug in 1. We'll get pi. We'll get 1/3 minus 1/5. Minus, plug in 0, it's all gone. What's 1/3 minus 1/5? It's a number, yes. 2/15. So you could say 2/15 pi. Pretty nice, huh? If we were able to rotate that thing around the x-axis and get this three-dimensional solid, then we could actually compute its volume by that integral. All right. So we're going to move on. I'm going to do the exact same problem, all right? I'm just going to change one thing now. Ready? I don't want to rotate about the x-axis anymore. I want to rotate this thing about y equals -3. How does that change the problem? My axis of rotation is no longer the x-axis. Y equals -3 is a vertical or horizontal line? Horizontal line, down 3. Is that rotated around this line different than this rotated around that line?
Not by much.
Are you going to get different volume?
Yes.
So let me try and convince you. If I rotate this right now around the x-axis, right? If I rotate this around the x-axis, do you agree I'm going to get something that looks something like this? And if you were to be able to see through it, you would have something like that. That's like a three-dimensional, this thing rolled around. Got it? Could I punch my hand through it? No, because it would pinch off here at the edge, right? If this rotates around, I would not be able to put my arm through this object. However, if I rotate it around a line down here, then it's got to come all the way around, right? Come back through the back side of the board and come up. So now I'm going to have an object that looks like this. And if you could see through it, it would look like that. Do you see the difference? I could put my arm through this. That's definitely going to have a different volume than that. Do y'all see it or not?
I saw it in the equation.
What's that?
It was in the equation also that we just saw.
What was in the equation?
Because if you plug in, instead of plugging -3, instead of 0 and becoming 0, you plug in -3 and you get a number.
Yeah, let's see how this impacts the formula. This is going to require some work. We good? Ask a question. You sure? I could jump through that probably on a good day, right? Not that one. All right, let's see how the picture looks here. All right, so I go through and I redraw the whole thing. All right, there it is. But now I put my axis of rotation down here. On the exam, you are going to have to draw everything. All right. So there's my axis of rotation. And everything else is exactly the same, right? So I'm going to bring my axis of rotation over here. I forgot to put my little arrows, curvy arrows here. I'm going around there. So I'm going to rotate around this. I'm going to bring my rectangle over, which is way up here. And then very, very important, I'm also going to bring the x-axis over. All right, that's my x-axis. Now, what are the things we need? R in, R out. We need the outer radius and the inner radius. So you're standing on the axis of rotation, and you break out your measuring tape, and you want to measure from here to the outer edge of the rectangle. So I am curious to know, what is this distance, right? That's R out. And then the distance, I'm kind of moving so I can leave myself some space. From here to here, isn't that R in? Do y'all see those two things? I need those measurements. So let's start with R out. What's R out? Well, the distance from here to here is x. I agree with that, right? From here to here is x. But then from here to here is 3. Now, I realize it's -3, but if I were measuring that distance, that would be 3 units, right? So instead of being just x, I also have to tack on the +3. So I could draw it this way. From here to here, that's x, but from here to here, that's 3. So R out is x plus 3, or you could write 3 plus x. It doesn't matter. Do you see that? That's why it's important to bring the x-axis over, because the x-axis is telling you, hey, look, this distance is just that function there. That function is x, so you have to tack on the 3 if you want your radius down there, or your axis of rotation. How about the inner radius? This is still 3, right? And this piece is x squared, isn't it? That little piece there. That's the bottom edge of this. And that's x squared. So what's R in? X squared plus 3. And at this point, I'm ready for the formula. The volume will be pi integral blah, 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 right? The volume will be pi integral 0 to 1. Still going to 0 to 1, right? Because we want to be moving that rectangle left and right, creating our